Hi everyone, hope you are doing good. This is Mahesh. In this video we will learn about big O notation. So in the previous videos we understood how the efficiency really does matter in any algorithm, and also we understood that we cannot measure the efficiency simply by writing the algorithm and running that algorithm in any computer because the efficiency of algorithm depends on the size of the input, or basically the input whatever we give it to the algorithm. So for us, this big O notation, it is useful in defining the efficiency by providing the order of an algorithm. So basically this is nothing but the upper bound on any function. So big O notation is nothing but upper bound on any function, and this simply tells us the function does not grow faster than this upper bound. So let us consider two functions, f of n and g of n. So say for example f of n and g of n. We say f of n is equal to big O of g of n if there exists constants c and n naught such that f of n is less than or equal to c into g of n for all values n greater than or equal to n naught. So this is basically a book definition for the big O notation. So what it simply says, it says this f of n does not grow faster than this g of n. So let us consider one or two examples and try to understand how this works. So we will keep this formula in mind and let us take example. So let us consider f of n is equal to 2n plus 5 maybe, and g of n is equal to n. So according to our big O notation formula, so f of n should be less than or equal to c into g of n. So that is nothing but 2n plus 5 is less than or equal to c into n. Okay, so if you look into these two functions, when this term will become lesser than this particular term, here the max term is 2n. So if this term is greater than 2, that time automatically this term will become less than or equal to this term. So I will assume c to be 3. So if c is 3, then this becomes 2n plus 5 is less than or equal to 3n. So what I will do, 3n minus 2n is greater than or equal to 5. So that is nothing but n is greater than or equal to 5. This value is basically called n naught. So n naught is equal to 5. So according to big O notation definition, this function f of n becomes less than or equal to this g of n at n naught equal to 5, and c is considered as 3 here. C is considered as 3 here. So you can consider even bigger value here, that is not wrong, but let us try to take the smallest possible number with which this condition satisfies. That way it becomes easier, and it is always good practice to consider the smallest number. So with this, what we understand, f of n is big O of g of n, that is nothing but f of n is equal to big O of n. So this is asymptotically we say f of n is of order n. Asymptotically f of n is of order n. So this is the big O representation for this particular function. Okay, so maybe what we can do, we will try to understand this little bit more by substituting some values for these two functions. Okay, so I will simply remove this. Let us take n value and f of n and g of n. Let us take different values. So let us assume n is equal to 1. So f of n becomes 2 into 1 plus 5. 2 into 1, 2 plus 5 is 7. And g of n is nothing but 3n here. So 3n here. So n is 1. So this value is 3. Let us take maybe 2, or instead we will try with 5, because we want to use these values to draw a graph later. So that's why. So now if I take 5, this becomes 10 plus 5, 15. And since this is 3n, this becomes 15. So we also learned here, right, at value n not equal to 5, this particular function, it becomes less than or equal to cn. So we can see that here. So this value, this particular value became equivalent to cn when this value n naught is 5. So that's what we can depict from here. Now let us take one more value. Let's take 10. So if I take 10, it becomes 20 plus 5, 25. And c into n, 10 into 3, that is 30. Let us take one more value maybe. So let us take 15. 15 2s are 30, 35. And 15 3s are 45. So with this table only, we can understand at value this is n naught. So for all the values greater than n naught, this fn will always be lesser than or equal to gn. So we can see that here at 5 this became equal. After that, everywhere it is less than the g of n. So how we can, we can show this on a graph as well. Let us try to draw the graph. I will remove this. Let us assume this is our graph. Maybe this is 5, this is 10, this is 15, yeah, and so on. This is n on this axis, and on this axis let us try to draw fn and gn. Just to differentiate, on this axis this is 5, so we have value still 45. So this is 10, this is 15, this is 20, 25. I will make it a little bit smaller. This is 30, 35, maybe here it is 40. Let us say. So when the value is somewhere 1 here, because this is n, this value is somewhere here 7. When it is 5, this is 15 here. When it is 10, it is 25. So when it is 10, it is 25. When it is 15, it is 35. So it comes somewhere here. So this is our f of n. This is our function f of n. Now let us try to draw it for g of n. So I will use black color for that. So when the value is 1, it is 3. So somewhere here. When the value is 5, it is 15. So here it collides. When the value is 10, it is 30. So somewhere here. And when value is 15, it is 45. Somewhere here. So if we see the value gn after this particular value, this is n naught. this Gn grows always faster than f of n. So basically what we need to understand here, so Gn gives us kind of worst case running algorithm, worst case time of a algorithm. So that's what I mean this big O notation represents. So there is no point in measuring the running time of an algorithm. Instead, we try to analyze how what is the growth function or what is the order or what is the big O notation of a function. So asymptotically, what we can say, f of n is equal to big O of g of n in this case. Okay, so this is one example. Maybe let us consider one more example to understand this one a little bit more. There I don't go in depth with respect to graph and such kind of table, but let us see. Let f of n be 2n square plus 5 and g of n is equal to n square. Then according to the formula, f of n is less than or equal to c into g of n. So that is nothing but 2n square plus 5 is less than or equal to c into n square. So we saw in the earlier example, so this term becomes greater than, I mean for this condition to be satisfied, this term should be greater than this particular value. We can consider more also, that's not an issue, but that will be suitable here. So I will say c equal to 3. Okay, so 2n square plus 5 will be less than or equal to 3n square. So if I send this, 3n square minus 2n square is greater than or equal to 5. So n square is greater than or equal to 5. Instead of 5, let's consider this as 4. So for this, n value will be greater than or equal to 2. So here n naught will be 2. So according to the formula, this particular function f of n is big O of g of n for c equal to 3 and n not equal to 2. So for all the values greater than 2, this Gn is always greater than f of n. So this gives the worst case running time of this particular time function f of n. So that is what we can understand through this example. So that's it for this video. In the next video we will try to see what are the different, I mean how to find the big O, the order of the order of a particular algorithm for loops. Yeah, that's it for this video. Thanks for watching the video.